This video is about breaking and forming bonds and how enthalpy is related to those processes. The first thing that we're going to talk about is probably going to be a little bit of a review for you, and this has to do with the enthalpy change that's required to break up a covalent bond. This is going to be reported in tables as an intensive property, so on a per mole basis, usually it's kilojoules per mole. And these are averages. It's important to realize that not every particular kind of bond is going to have exactly the same bond energy. For example, if you have a compound that has multiple OH bonds in it, once you break the first OH bond, the others will be easier to break. So these are averages. And that means that they're going to be a little bit off from the experimental values, and you can only really use them to make estimates. Another thing that's true, as we know, they increase with the increasing number of shared electrons. So as the bond order goes from 1 to 2 to 3, single bond, double bond, triple bond, it's going to require more energy to break up that bond because there are more attractive electrons that make it up. And then it's a positive number to break up bonds because that's an input of energy for the process. But when bonds form, it's the opposite sign. It's a negative number for bond energy. So overall, the process is you take the bond energy for the reactant bonds, multiplied by the number of moles, because remember these are intensively reported, and then subtract from that the bond energy for the product bonds, and that gives you an estimate of the delta H value for the reaction. So for example, we could use bond energies to estimate delta H for this reaction. Let's go to a better space with more room for working and solve this problem. When solving problems like this, it's important to draw Lewis structures for everything, if you don't already know what the Lewis structures are going to be. And the reason for that is because it's important to know which bonds are actually being broken and formed. If we do this for NH3 up here, we've done this before a bunch of times probably. That's what the Lewis structure looks like. So those are single bonds. For oxygen, we've drawn the Lewis structure for oxygen before. This ends up being a double bonded species. And CH4, again, this is another species that we have probably done the Lewis structure for more than once. This ends up being single bonds between the carbon and all the oxygens. HCN, when this Lewis structure is drawn, the central carbon ends up being triple bonded to the nitrogen. And then, of course, it has to be single bonded to a hydrogen. And then water, another one that's very common, single bond to an O from two H's. Okay, so for the energy that's going in, this is the bond energy that's going to be the positive number, we're going to have 6 moles of NH bonds because we have 2 moles of NH3 and each one has got 3 moles of NH bonds. And if we look on the chart, I just grabbed this from our textbook, this is 390 kilojoules per mole. And these bond energies are readily available in lots of different sources. Oxygen, we're going to be breaking up 3 moles of OO double bonds. So that's right here, 498 kilojoules per mole. And then we're also going to be breaking up 4 times 2 is 8 moles of CH bonds. And a CH bond is 415 kilojoules per mole. So that's the energy in, and then the energy out, so this is the negatives, will be 2 moles of CH bonds. CH we just did, that's 415 kilojoules per mole. And 2 moles of C triple bond N. A C triple bond N is 891 kilojoules per mole. And 6 times 2 is 12 moles of OH bonds, and an OH bond is 464 kilojoules per mole. So when we put that all together, we get a negative 1,026 kilojoules for this process. Now in a previous video, we solved this exact same question using heats of formation, and the answer that we got was actually negative 940 kilojoules for this process. experimentally determined. So this is only an estimate, this value, because remember that these bond energies are averages, and so they're always going to be off a little bit. Our last topic in this video is about the Born-Haber cycle, which is a way to find out what lattice energy is. It's usually impossible to directly measure lattice energy. And so what we do is we use an application of Hess's law that allows us to find it. And this is basically how it works. If we have energy on the vertical axis here of a sort of a diagram, the lattice energy is literally the energy that's released when gaseous ions approach each other and get close enough to make the ionic solid, that lattice crystal that makes up the solid. That's the lattice energy. But we can look at it from a different standpoint. If we start out with the free elements that make up this ionic solid, we can think about this as having several steps where the free elements ionize and turn into gas, if they aren't already, that could be added up by Hess's law. And then we can also use the experimentally determined heat of formation and make a combination here that allows us to find the lattice energy, because the lattice energy is going to be the sum of all these several steps, which are going to be positive numbers, and then subtracting the heat of formation, which for ionic solid is typically going to be a negative number. So here's an example problem that will help us see how a Born-Haber cycle works. Let's go to a space that has more room to work and solve this problem based on this data. So our starting point in making this Born-Haber cycle diagram is to start out with solid magnesium, because that's magnesium in its standard state, and oxygen as a gas. And we're going to make MgO, that's going to be down here, in the solid state. And delta H of formation for this process, it says up here, is 602 kilojoules per mole. And I've got a downward arrow. I'm going to leave off the unit here because it's a negative number. To make 1 mole of MgO, I would have to have a half a mole of oxygen gas. Now to find the lattice energy, I have to get myself up to magnesium 2+ ions in the gaseous state and oxygen 2- in the gaseous state. I have to get those ions in the gaseous state. And the difference between here and here, that's the lattice energy. That's the thing that I'm missing. Well, one thing that has to happen is my magnesium has to become a gas. So that's going to require an increase in energy. That's the enthalpy of sublimation of magnesium. So that's a 150 kilojoules of energy added. Then I'm going to have to ionize the magnesium. That's going to require 2 magnesium ionizations. So I'll go to Mg plus as a gas and 1/2 of an oxygen molecule. The first ionization energy of magnesium is 735 kilojoules. Then I have to ionize it again. So to get to Mg2+ gas and half an oxygen gas, that's going to require the second ionization energy of magnesium, which is 1445 kilojoules. Then I have to break the O2 bond to make an oxygen atom. So getting up to Mg2+ gas plus 1 O atom in the gaseous state. The bond enthalpy is what I have to overcome there. That's 498 kilojoules per mole, but I'm only doing this for half a mole. So this increase is 1/2 of 498 kilojoules. Then I have to ionize my oxygen. The first electron affinity, which takes me down to O1- gas with my magnesium 2+ gas ions, that's right here, first electron affinity. It's a negative number, so that's down 142. And then the second electron affinity to get me up to oxygen with a 2- charge, that's a positive number. That's 878 kilojoules. Now this is not all to scale. but it gives me kind of a layout of what I'm going to have to do to find my lattice energy. So to get from here up to here, I'm going to add 602 kilojoules, then another 150, then another 735, then 1445, then half of 498 kilojoules, and then I'm going to take away 142, and then I'm going to add 878 kilojoules. When I sum that all together, I find out that the difference between the ionic compound and the ions in their gaseous state is 3917 kilojoules. So that's the lattice energy.